We have so many. Okay. Yeah, so, okay, guys, we start our lecture. Yeah, this is a DAA class C, and then everything you can see in subakti.com. So this is, I use this, and then this should be the first one because it is team teaching. Yeah, through these courses, you will see Pak Buti and me. Yeah, so the first lecture until the fourth is Pak Buti, and then me. So I will give you a lesson in lecture 5 until 8. Then continue Pak Buti again, yeah, Pak Gus Buti again. And then the TA, teaching assistant, is Mas Samsutuha, yeah. Everything I put in here. So it's about our schedule in Wednesday should be this IF 104 if it is offline, and then 1 until half to 4. Yeah, I mean this official schedule. And then we have two reference, Corman, and then this community programming. Actually, I think Pak Buti already told about this. And then I asked Pak Buti what's going on, and he told me that Pak Buti already taught you about introduction and getting started, and then getting started should be getting started. Yang itu. This is class C, yeah. Getting started. Where is that? Yeah, started. Getting started. Yeah, I update. And then also it is should be chapter 2, yeah. And then growth function, growth of function. And then the last chapter, the last lecture should be standard notations and common functions. Yeah. Then divide and conquer, yeah. And then quiz, the first quiz, right? So today we will discuss about sorting, sort and quick sort. And then as usual, I usually give the QR code in here, so everybody can just simply key in or can use your camera, yeah. And don't forget to fill your attendance list or tick, yeah. But if you got any problem, just let me know. Because usually somebody forget, yeah. Somebody maybe got ill or something. Just I don't want you to have any problem about this attendance list thing. Yeah. Okay, so my plan only have for lecture only this sorting, sort and quick sort is all in coming minute, and then FEL3 and dynamic programming. Actually, the focus is dynamic programming. Yeah, before we got midterm. Yeah. So midterm is the something like this. But I know there is some announcement that I test. I remember 14 or 16. I remember because that Bu Ika just told like 12 until 16 cannot get. Should be off day. Yeah. What's going on? I don't know why this 12 until 16 cannot go. Yeah, this 12 until 16 is, yeah. Oh, that because of the first of bulan puasa, what, yeah. But to me it doesn't make sense, yeah, because anyway we are in home. Yeah? So if it is cannot, it mean it is for that because basically we only have our lecture in 14 in Wednesday and Thursday, yeah, 14 and 15. So usually if cannot, for instance, because it's really ridiculous, yeah, if we cannot, for instance, in 14, because we have actually schedule here, yeah, it's in 14. Because then we can discuss in our WhatsApp group, guys, yeah, that's why I very like to have this, yeah, if it can, yeah, for instance, if it can, it's up to you. I mean, if it is, we insist 14, actually nobody prohibited us, right? But okay, because ITS want us cannot, yeah. So 12 until 16 and 26 until 30 April. Yeah, we can, for instance, make up, yeah, have a replacement lecture, for instance, in 17, yeah, because 16 cannot, yeah. So we need 17. Usually I have a makeup class or makeup lecture in Saturday, yeah, or even also Sunday also okay, yeah, because it's a 12 until 16 cannot. Really, for me, guys, actually it's quite, in the reason, for instance, if we are starting for fasting and then we need to have a preparation, it really doesn't make sense, you know, when you can ask Pak Putih also, when we are in abroad, there is such kind of thing, yeah, if it is, there is no holiday for fasting when Ramadan or even for Idul Fitri, yeah, we still have to go and so okay. So there is no, I mean, all of the restaurants still open, and then you can also see people with, for instance, very very minimum clothes. Yeah? I mean, with bikini. I mean, it doesn't make sense that it is ruin our fasting. For instance, for me, it's okay. You can ask Pak Buti also. These are for me in the beginning of puasa Ramadan. Then we have to go for holiday like this. Like, what's going on? I mean, that's why I like. Uh, because me really I want to be to have to see, yeah, our nation is have a develop like others. But if you like this, then when, yeah, we have too many holidays, too many relaxed time, while other nation already catch up. They are competing to conquer Mars or Moon, yeah, and then we still even starting for starting of our fasting puasa, and then we need to go for holiday of day. Yeah. It is can, yeah. So I think I will change. Of course, I will keep announcement, yeah, in our WhatsApp group. In our WhatsApp group, maybe let's say 17, yeah, Saturday, yeah, from usually from 7, yeah, 7 until 9:30, and then 9:30 until 12, like into class. Then maybe istirahat, yeah, take a rest for a while, and then 1 till 3:30, and then 3:30 until 6, yeah, okay, 1 day, yeah, to catch up everything. Yeah. It's very ridiculous, yeah, this that we cannot go. And then what's the other one is uh 26 until 30 April, yeah. 26 until 30 April. Let's see. This is this, yeah. 20, this is 21. So it mean okay, yeah. 21 is before, I think it is before Lebaran, right? Before Lebaran for Idul Fitri. So it should be okay for this. Only this, yeah. We need to catch up. Uh, Even actually, maybe many of you already know that usually I even have speeding class that I have 2 lectures every week, not just one. So in 2 months, and then I finish. Of course, I believe the understanding may be not so high like that normal class in 16 weeks because only 8 weeks. But it's not that bad because it is been proven that my student in this speeding up class is not that bad, even though it is only 8 weeks comparing to other who got normal 16 weeks. It's comparable. The achievement is comparable. I never claim that my lecture and my student will be heavy weight champion world class like in Pak Ruli, class A and B, but also not bad. That's why if there are too many holidays like this, yeah, and it's really feel me really ridiculous, yeah. It should be, if it is possible, as soon as possible, yeah, finish and then you can enjoy, guys, yeah. For instance, before Ramadan, if it is finished, before Lebaran, it is good that you can enjoy Idul Fitri fully, yeah, without any thinking about we still have a class and so on. Yeah. But that's the way. Yeah. So, and then for midterm is 28. Yeah. What is it? It's 26 until 30 April. Yeah. And then you see, it's going to become uh, because, yeah. So it mean where is it? Midterm, yeah. 26 until 30. Okay, I will just put it here and here, yeah. All the time. See this with this, yeah. So it is off day. Off day. So it means this, yeah, and this is okay, and 1. So today okay, yeah, because it's only 7 April, but for FEL3, yeah, still need to catch up. Because it was I planned 14, yeah, because I planned a long time ago actually before this, and then cannot, right? So cannot. So it means we have to to find another date, right? So let's say 17. Of course, it can be, yeah, it can be after Ramadan, but I don't like this. If it is possible, yeah, just make up as fast as it can, right? This is for FL3, and then dynamic 21, yeah. So okay, 21 still okay, yeah. So this is 21 April, 31st April, okay, yeah. This is okay, right? Uh-huh. This is not okay because I plan 28 is actually midterm exam. Yeah. What the hell like this? Yeah, I really don't I don't really don't get it. Yeah. This cannot, yeah. Cannot. Remember guys, yeah, all of our assignment will be open book and then 1 week, you take home. So it's really so if 28 cannot, until 30, yeah, until this cannot, yeah. So it means become first this May, yeah, first May, okay, first May. Yeah, so become first May, yeah, May, okay. So this roughly like this, guys, yeah. This for class C, and then as well class D, then yeah, class C. Even before we start our course, yeah, it's better to preparing like this. So I plan maybe like this, yeah. But as usual, because we have I teach class C, D, E, F, and then IUP, yeah. So it is up to you guys. You can choose any convenient time. Yeah, this officially inshallah yeah for that midterm this, but it is online. But even usually I even give wait. Even I give the question usually at late some hours before, but usually even a day or 2 days before. Yeah, also can give this. So this should be okay. So then if class C, yeah, it's also very tight for me actually. If only 1 day, for example, Saturday, yeah, we have a makeup class. So this it means class D become 9:30 until 12, yeah. Then this right, CD, and then it is only for like because anyway this for exam is take home until like this for instance, yeah. D and then CD. What I got class CD E, yeah, class E, because DE actually is my class. Yeah. Because if DNE, wait guys, yeah, so just give me time to have a plan this class E, because it's better to have a plan and then yeah, like this, yeah. Mm-hmm. Okay, so 15 also cannot, yeah. Cannot 15 also cannot. So class E, then gosh, it's just become mess, yeah. So 15 cannot, right? And then 28 and then 20 to 29, yeah. Yeah, 29. So cannot, then cannot, yeah. So, okay. So this is become, let's say, it's really very tight for me from morning. I'm just talking until Maghrib, yeah, until Maghrib time. Yeah. This, all right. ahead. So okay, because this should be, yeah, this is with 17 April, yeah. So this is 13 until this. Yeah. Midterm exam, it doesn't matter, yeah. So everybody in when may, but to make it official, yeah, official date, I just put it like this, okay? Wait, 1530, and then IUP, yeah. What is IUP? Wait, need to see IUP. I just realized today that, wow, actually my goodness, there is a IUP. What time usually IUP is 9:30, yeah, 9:30 until 12. And then class F I already finished. E, okay, 9:30, okay. So this is IUP. Wait, give me time. Okay, guys, yeah, IUP. So this is 15:30 until this, yeah. Well, of course, if we are tired, yeah, and then both of you tired, then maybe it's no need 2.5 hour, yeah. Because it is officially we have to uh, think like this then, yeah. Okay, this is okay. This is midterm, yeah. This is midterm, and then this also midterm. This also midterm, and you guys should be here. Okay, yeah. Yeah, that usually I try, guys, yeah, to catch up, yeah, to catch up this situation. Yeah, this is yeah, this that's the one that I really don't like actually. That for me, it's better to have how to say the class, yeah, just like what it should be. But of course, ITS, I mean, they have their own, yeah. So I mean, roughly like this, yeah, maybe. But of course, I will give you announcement in our in our WhatsApp group. Okay, back to class C. Okay. So because of team teaching, yeah, of course, I cannot control of the class. So I only can control, for instance, your performance in lecture 5 until 8, yeah. So I mean, only for the midterm, yeah. And I think all of you guys already know that uh, I don't have any body feel in my class, yeah. So everybody just pass, yeah. But before that, you should just remind, yeah, because it's the first one we are meeting, yeah, that we have to start uh, our lesson here, yeah, our lecture here by uh, our willingness, yeah, that our willingness. Yeah, that I really wish that it is for our worshiping, yeah. And it means everything we are doing, it become credit to our next word, yeah, our nether word, yeah, after the next life, yeah. So this would be like this. I know it is not easy. It's difficult, and especially we got many problem in recent days about pandemic, that everybody got stressed, and before we thought our socialization, yeah, then our life is really so difficult, isn't even me. So the last time I went to ITS after 1 year, more than 1 year, is last Saturday, yeah, because they got they give us jab, yeah, for vaccination, yeah. So all of the lecturer and also employees in ITS got, and after 1 year, of course, I'm so miss our campus, our classroom, and everything and everybody. Of course, nobody there when I come. I just come to my room and see my room what's going on. And then tomorrow take the jab, yeah, then got vaccine, and then right away. So I come in Friday night and Saturday got jab, and then right away I back to Magetan. So but anyway, when we have our willingness or our niyat, yeah, that it is our worshiping, ibadah. So everything we are doing, yeah, from morning you are wake up and then go to the campus, and not even go to campus through online, yeah. It seems to be your credit. That is our strong point, our virtue. Yeah. And then secondly, everybody pass. I mean, at least because I only have a responsibility in your 4 lectures, yeah. So everybody pass. So pass, not pass away. So pass, not pass away. Yeah. Not pass away because I want you to live longer than me. Longer, healthy and happy. Yeah. Not just longer and you got so many things. Yeah. Okay. Not pass away. Yeah. So at least because I have to say at least your midterm, right? Yeah, your midterm, great then, yeah. But I believe Pak Putih also nice, yeah. It is your senior. What is Pak Putih? 2009, yeah, 2009, I think, yeah. The same like Pak Isat, 2009 in undergrad enroll. At that time, I already in what is 2009? Still in Taiwan or just still wandering in Europe? Okay. And then I always everybody. I mean, this everybody. I mean, student, yeah, student. I mean, because I talk to you. Yeah. Then have a high grade. Yeah. I don't like to give a very stupid grade. Yeah. And then, yeah, just having fun. Yeah, having fun. Lecture. This my wish for you. Yeah. So you can check also. Uh, let's see web programming. This is the last one I give class. Yeah. So check the grade. I never think it to give you a grade. I want you all to get A, yeah, but some student doesn't want. So it's really very weird. I want you have all to get A. Yeah. I mean A. Yeah. Check this, guys. Yeah. But unfortunately, see, yeah, I don't want it because all of my student, all of my friend got A. I wanna the only one got AB. And of course, I cannot force him or her. So I want actually perfect score. Yeah, 100% got A. Yeah, but anyway, there is somebody doesn't, so only 97%, unfortunately. But it happened in the past. I all of students got A, so it's perfect score. And then even the directorate doesn't like. I mean, they criticize me that, Irwan, how come you give your student all got straight A? And I said, no, see, some even got A, B, or maybe even BC as a default. Default is BC. So even you are the laziest one, the lazy phone one, you got PC. No, no, but it's not all got A. Some even got submit to some journal or conference or paper. Yeah, then but usually 3 months also we finish our work. Okay, okay, this thing, yeah. I mean for our introduction that it should be not difficult at all. Yeah. Okay, so let's right away go to our first uh, lecture this, yeah. So you can check this, yeah, and then we have WhatsApp group, yeah. It's very easy now. That what is that? DC, yeah, yeah, yeah. And just discuss this. Masam Sutuha, yeah, will help you. Yeah. Usually, TA will respond first, yeah, because sometimes we are lecturer so busy with so many things. Because remember, we are not 8 hours working; we are 24/7. Yeah. Sometimes kind of thesis or that practice work, yang kerja praktek or that was that the student creativity program PKM or something. Pak, please revise. Okay, okay, just send to me and then I will revise. Pak, but the deadline is tonight, 12 o'clock. Oh really? Yeah. Oh sure, sure. Yeah, because usually in Monday, in weekend, Saturday or Sunday, I mean 23:59. I mean in the middle of the night, 1 minute before early morning uh, in Monday. Yeah. So I also have to stay awake, yeah, with you guys, I mean student, and then okay we proceed. Yeah. Of course, some maybe can be accepted, some not, but it doesn't matter. The most important is that you show your achievement, your work, yeah, and that's the thing. That our good Lord is appreciate your achievement, your work. For the result, let him. It is his part, but our part is working to our best. Yeah. Okay. Yeah. So this guys, our plan. Okay. So this, yeah, and then just check it out. Yeah. So lecture 5. Yeah. Lecture 5 is about sorting, keep short, and quick short. Okay. It's the PowerPoint like this. Yeah. Okay. Okay. Comment tools, pencil. Okay. So sorting algorithms. Yeah. And then we learn about heap sort and quick sort. Heap sort, you have heap data structure. So actually the series data structure is like almost like stack, yeah, but it's not like stack, yeah. Heap data structure, and we also will discuss about priority queue, yeah. And everybody should be already past the data structure, right? Data structure, TS. And then the core of data structure is abstract data type. Yeah. Usually also, but we also ask you this, yeah, what is the core of data structure, guys? And then on these three word, three character, EDT, abstract data type. And then we also learn quick sort, this very popular algorithm, very fast on average. Okay. Okay. Why sorting? And why sorting? Actually, for this semester, like Paruli actually won maybe not so many material, yeah, but because we try our best, like how to do. So actually, the material is maybe not so many this year. Maybe only this actually, yeah, this. But the thing is, the focus now is only I mean, it's with dynamic programming, you know. I mean, our partner. But if directly there, I think also a good idea to add up with something. Yeah, that's why I try to combine what is the material for this this semester. Yeah, combined with the previous year. Yeah? Okay. Why sorting? Yeah? And it's very good. Is when in doubt, sort. I think also can be applied in our life, guys. So if you are in doubt, yeah, you are not certain, it is uncertainty in your life. Sort. What is sort? I mean, you are tidying up, yeah, your life. And usually I also do it this. Yeah. So if I'm not certain about what's going on, yeah, it's better to do something. Yeah, you cannot just do. I I have a doubt about something. There is uncertainty, and then you do nothing. In this thing, it is better to short, yeah, to tidying up, to what to say, put order in whatever you are doing. Yeah. And it is actually one of the principle in algorithm design. When it does short, so it means you are preparing your thing before anything happen later. Yeah, like also, you also can call it proactive. Yeah, you proactive. You already prepare. You have prepared for everything coming in the future. Okay, so this is one of the principles in algorithm design. Sorting used as a subroutine in many of the algorithms. For instance, searching in databases. We can do binary search on sorted data. That's why, yeah. Okay, for instance, this if linear search, yeah. Okay, just image, easier image, yeah. What is this? If this array, for instance, I have array, yeah, and then you have a random element or random number in there. For instance, you have a random number or random element in there, yeah. Of course, you don't have any other ways, yeah, to search, for instance, to search. That means you get only linear search, right? Then like take a look in this, yeah, in my cursor. So because it is random, I mean there is no order at all, yeah. It's not been sorted, so it means you only have one way to search some particular element or item or a number in there by what's like linear search. Then it means what? It means you have to spend, yeah, what's that, big O, N, then yeah, big O N, because there is no other way. Yeah, there is some, there is no certainty that, for instance, the one that you are looking for is in the first, the worst, of course, in the end. Yeah? The best in the beginning, in average, in between. Yeah, but with which one, nobody knows. That's why, and then big O N for the worst case. But if it is sorted, yeah, then you can use binary search. Yeah, binary search. But remember, binary search, it means you already been sorted. Yeah, already been sorted. This, yeah, is already sorted. Doesn't matter sorted ascending or descending. This case is ascending, yeah, from smallest one into the largest one. Yeah? So it can be seen, yeah, if it is sorted, then everything will be easier. That's why also can be used, for instance, in the big data, yeah, in Facebook or any social media, right? Instagram, Twitter, Snapchat, WeChat, YouTube, even YouTube, yeah, for graphic. There is a sorting one, but of course there is some kind of mechanism, yeah. So it is not so-called random. This is something like order, yeah. It's sorted in some particular order, and then when we want to find anything, we make it very very fast. Yeah? For instance, uh, uh, ikatan cinta is the phenomenal only 0.60 second. Yeah, was that was that was then Lisa, Blackpink, only 0.68 second. Yeah? So it's very, very, very fast. Yeah, you can imagine like it's a big data from 57 million. Yeah, sorry, it can give you 57 million result. Of course, of how many we don't know. Yeah, because Google got a series of server, yeah, you call it farm of server. Yeah. Can you imagine if there's no particular order, there's no sorted thing, then how to find so fast? Yeah, it's many things. Mawar Eva de Jong, yeah, 0.78 second got 388,000. Yeah, of course. Was that Lee Min Ho? Yeah, your favorite. Okay, your girls. 0.71 second, 277 million result. Yeah, of course, there's also some in Indonesia, resemblance by Mas Liminho, yeah. This another one in which that in Samarinda, yeah, and so on, yeah. So you can see like how what is the power of sorted data, yeah. And then it's very very powerful. It's kind of like a preemptive, yeah. Before you are attacking somebody, you're preemptive attack. Even you are proactive, you are prepare something. This why when in doubt, just sort. Then a large number of computer graphic and computational geometry problem, of course, we'll use this. If anything, PUBG or whatever, yeah, was like for the collision detection, yeah. PUBG, of course, I think also use uh, collision detection, yeah, call collision detection. This, yeah, there's many things, yeah. In computer game, of course, also many paper about that. Huh? And computational geometry, I think tracing like ray tracing, and so on. Yeah, this is many things that you need to sort first to make to what to say to make your task easier. Yeah, and then another one like closest pair. Yeah, closest pair. For instance, if you are in, you can imagine that you are a programmer, and then you need to develop an algorithm. Let's say with sport games, and uh, that if you wanna, let's say it's like a strategic game, like I don't know, maybe like Tycoon or maybe like Warcraft or Minecraft or whatever, yeah. So like closest pair when you click, and then when you wanna group some that like some actors or some player in there, yeah. You make it a group, and then which one like closest pair? Which one is the close one? To distinguish between the hero and the enemy, for instance. Many things, of course, yeah, in computational geometry. Element uniqueness. Yeah. So you how to sort some particular elements by this uniqueness. Then frequency distribution is kind of example. Okay, and then so still why sorting. Yeah, a large number of algorithms developed representing different algorithm design techniques. So of course, different algorithm have different approach, yeah, for technique. Usually for the lower bound, yeah, for this lower bound, remember, yeah, big omega. The lower bound is something in here, yeah. Okay, let's say this is upper bound. So this upper bound, it would be this is lower bound, yeah, yeah. So lower bound is by big omega, yeah. Upper bound is by what big O, yeah, big O here. And then in between, yeah, tight bond, yeah, by what big, yeah, tight bond, EB, yeah, tight bond. So lower bound it mean for the best case, yeah, best case. Yeah. So best case is big omega and log n, is to prove lower bound of other problem. Because so far, yeah, the best algorithm in best cases n log n, big omega and log n. Okay. Okay, sorting algorithm so far, I think Pak Budi also already had taught you about, yeah. So you have insertion sort. Insertion usually for the playing card, yeah, playing card can be seen in insertion sort. Just usually I just put any in Wikipedia and then check this, yeah, this, yeah, see, yeah, this is like in playing card, yeah. So usually I sort from the smallest one until the largest one, yeah. That means easier. For instance, in playing card, yeah, 2, 3, 4, 5, 9, yeah. 2, 3, 4, 5, 6, 7, 8, 9, and then after 9, yeah, and then you have that 10, yeah, then, yeah, then you have jack, yeah, q, queen, 4, and then king, and usually we sort, yeah, which one, because we also have a spade, yeah, club, and diamond, yeah, I mean, for the type, kind of the flying card. So then you want to sort it out, yeah, because if you are not sorted, you make it messy in random, maybe you will take the wrong card, yeah, when you are playing. It doesn't matter what kind of you're playing. You are playing maybe bridge or maybe poker, yeah, many. That's why we need to sort it out, yeah, as a preparation. Yeah? Proactively, you are doing this, and then to make sure that it's easy for you, right? Okay. So this is insertion sort. Yeah, you need to insert, yeah, insert in particular order, and then that's why, and then the series of your card, yeah, can be sorted. Yeah. And then selection sort. Yeah, after insert sort, it's like playing card. Then selection sort. What is selection sort? Selection sort. This is Wikipedia. It's easy. And I love if there is a picture about that like this. Yeah. It is easy. I mean, for example, also ascending. Yeah. I mean, you will take, you find the smallest one or the least one, and put it. Yeah. And then it means if you put on the top, yeah, like in this case, yeah. And then the rest, you just easy to sort it. Yeah? Like that. Okay, once again, okay, 8, yeah, and then you're looking for, okay, 0, put it on the top. Yeah. And then as time passes, yeah, the domain of searching is become shrinking, right? Because 0 already got, yeah, place 1 also got that place 2 already got that place 3 and so on. Yeah? This is selection sort. So it means once you halt, yeah, for instance, the 0, 1, and then you don't need to revisit the 0, 1, only the rest of it. So in the beginning, of course, you need to look for the smallest one number, right? Then you cut it, put on the top, and then next, in the rest of that series of number, and then you look for again, and so on. This selection sort. How about bubble sort? We are not in the detail, but just see a bubble sort. Okay. See, the animation is easy, yeah. So it's like bubble, yeah. If you are put in the bubble, in the water. It's very simple one, yeah. Only kind of window, and just swap, yeah. So starting from beginning of the list, compare every adjacent pair, then swap. This is the most swap their position if they are not in the right order. The latter one is smaller than the former one in this case. And after each iteration, one less element, the last one is needed to be compared till there are no more elements left to be compared. And so on, yeah. So this is the first step, yeah. Okay. Step this, and then once again, you need to compare, and so on. And then you will get that sorted order. Yeah? Again and again, yeah. So of course, this thing is not that good. Yes, this for like worst case running time. Worst case should be like pico, yeah. Pico and square, yeah, in place. What it mean in place? Which means you don't need any additional storage, any additional array, yeah, to temporarily save your number. So this big O, yeah, but that's okay anyway. Big data n square, I mean the power of 2 is the worst case. Okay, you got merge sort, yeah. I think Pak Budi also already thought about this. Merge sort or merging. Okay. It is also simple. Just use that. Yeah. Yeah. You divide by 2, divide by 4, by 8, and so on. Yeah. Then if there's only one, then you can apply the order. If it is ascending, of course, you need to compare between this only one element and then which one, the smaller one, and put in the left, and so on. Yeah. Then after divide, yeah, until leave it when only one, then you need to conquer. Conquer is that which one is in the correct order, and then need to combine actually, yeah, the cost of combine until that sub problem back into the original like a big problem. Sorry, or that sub solution, yeah, back to that original solution. Also, it's easy to understand, yeah. Worst case running time, of course, and log n. Maybe you have 1 million, yeah, parallel processing, yeah, in a time, because we have 1 million core, for instance, yeah. You can imagine how fast. That's why you type anything, yeah, type anything in Google, and then right away it can give you a result, right? Anything. Pak Dul, yeah, 049, yeah. It's really fast, so really fast. Who is the assistant? Assistant. Okay, say beautiful assistant of Pak Dul. And oh, beautiful, sorry, beautiful, yeah. And then even image. You can check this, yeah. It's so fast. How many? 0.30 second, yeah. Image. Okay, this. Click, yeah. Then click, yeah. So fast. And then Avi Lasa. Yeah. So literally this merge sort is so fast. Yeah. Even though it requires or it requires additional memory. But in this era, in this time, when I was in undergrad starting my study like you guys, I remember only Pak Febrian Samopa, the lecturer of information system department. Is the one got the faster computer at that time. How many memory he has? I think 16 megabyte. Well, most of us only got 1 or 2 megabyte. Remember, not gigabyte. Megabyte is megabytes. Pak Yan got, I think, 16 megabytes, and he installed Mortal Kombat game, yeah, with that super VGA graphic, and so yeah, I'm so like quite amazing because usually we only have VGA or CGA or EGA, only 256 uh, kilo graphic card. That's very stupid, yeah. And then now you guys in your time, even your own cell phone, yeah, already in gigahertz. Yeah, it means everything memory also giga, even terabytes. Yeah, at least I believe that your cell phone have at least 4 gigabytes memory, yeah, and 2 point something gigahertz. Yeah, in my time only 16 megabyte RAM. Yeah, and then how many? 16 megahertz, maybe only 100 megahertz, and not gigahertz, and very very slow. Okay. Okay, this selection short, yeah, I think Pak Putih already discussed about it. Yeah. So we try to just a bit refresh your mind. Yeah, selection sort from array A, yeah, from index 1 until n. It is a kind of how to say, we call it natural index, yeah, 1, yeah, because okay, 1 until n, yeah, because when we come into our computer system, index started by 0, yeah. Because why? Because in state 0, this is already state, right? State 0, yeah, only was like 0, 0, 0, 0, 0, 0, 0, 0, 1, yeah. Sorry, 0, 0, 0, 0, let me only 3, yeah. This already state, yeah. And then, okay, 1, 0, 0, yeah. And then, okay, 0, 1, 0, yeah. And then 1, 1, 0, yeah. This already state in here. Why we are wasting this? This is like index in almost, as I remember, as I understand, all of the programming language will use 0 as the first index. But anyway, we talk about DAA that you just use 1 as the first index for natural index. Okay. And then for I equal to n down to 2, then find the largest element among this index, from A until in A from index R1 until I here, from n down to 2. Then exchange it with A index I. Selection sort. It's back again. Yeah. So yeah, Avilasa, you wanna pointed her, guys. Yeah, it's very beautiful and very smart. But anyway, core of the core is Pak Andul. Core of the core is Pak Andul. Yeah. Pak Ruli and I also confess that Pak Andul is our master. Me myself patronize Pak Ruli. When from I was student until now, yeah, that's why I always put myself the second one. Yeah, that's why like in many thesis, Pak Ruli become the first supervisor. I'm the second one because really is amazing. Yeah. Okay. What's got this? Yeah. Selection sort. Yeah. Selection sort. Yeah. Selection sort is the one that we are here. Yeah. Okay. This selection sort. Yeah. Okay. Selection sort. So you find the largest element among this. Yeah. Among this. Yeah. This is it. Mean what? It mean descending. Yeah. This is descending. This is descending. I mean this. The largest element among this exchange with this. Oh no, actually not descending. It is still ascending. Yeah, still ascending this. But to find for the comparison, yeah, the comparison, which one, right? And then you exchange with this. Find the largest element among this. Exchange it with AI. Yeah, AI. Yeah. So because it is from this, yeah. This is n, right? N. And this is, let's say this is 1, yeah, index 1, yeah. So he find the largest element among A until this, yeah. And then among A, index 1 until I. But the first I is N, yeah, here. Of course, it's only 1. Only 1, nothing to do. For instance, if you are comparing 1 as the last one here, yeah, the index 1, you yourself. But anyway, first one usually is will have a great work. Find the largest element among A, index I, index 1 until I, and then exchange it with AI. Because you can check this. A takes big data N, because you have to find everybody. It means that N, right? You can't avoid this. But for exchange, of course, it is constant. Yeah, that's why big data 1. This means constant. It is constant in only a particular time. Yeah. So in total, it means big data N square. Yeah, because remember this is N. Yeah, this is N, and this is N. You find N of N, it means N squared. Yeah. Okay. Let's just also check this. This. When it backs again, okay. 8, yeah. Okay. And 7, exchange. 9, 4, 5, 6, and so on. Again, 8. Then exchange with 0, yeah. 7, exchange with 1, yeah? And so on, yeah. And so on. It's quite easy to understand this, yeah. So we have idea for improvement. Use a data structure to do both A and B in big O log n time. Usually we just if log, yeah, then it is 2 base, yeah, 2 base n, LGN. Because if only log, usually people this is don't want to put it, but actually it should be like usually 10 base log. Yeah. Usually it is log. But anyway, it doesn't matter what kind of base in the sense of DAA. Yeah, the base is not bigger different. Remember, we always talk about big number. Yeah, big number. You can imagine if it is very big number, like number of atoms in universe is around 10 power 78 to 10 power 82. That's why I said it doesn't matter what kind of base in your log. Yeah, here it is 2 base log or 10 base log. Not so big different if we talk about this big number. Yeah, remember that's why we have. I think Pak Budi already taught you about asymptotic analysis. Yeah, it is not asymptomatic. Asymptotic analysis that we only deal about the big number. It means we want to get rid of the detail, yeah, and get the essence, right? Okay. So if we can improve like this, we need that's why we need to pass data structure first, yeah, actually to get this DAA. Well, actually, data structure can be later. You need to actually know about algorithm, yeah, design, analysis, and then you know the data structure. Because anyway, when we deal with data, you like or dislike, you need data structure. Then okay, you can do efficient programming. But as usual, it's be like this, yeah. So actually, you have to know about algorithm. It doesn't matter, yeah. First, okay, design and analysis, yeah. If like we become DAA, design and analysis of algorithm, yeah. And then, but before you can do for programming, you need data structure because anyway, if without efficient data structure, you cannot do any programming, yeah. And then okay, you can go do for programming. What kind of programming? Actually, it's about real life, yeah. And then you've got a problem in real life, right? And then real life problem, if can be solved by so-called computer, yeah. It means we call it computational problem, yeah. And then okay, yeah, this, and then you want to solve the problem like this, yeah. Programming, then it means solve the okay computational problem here, yeah. Problem. And yeah, of course, like solve the real life problem. This is kind of the how to say the order, right, guys? Yeah. And that's why in syllabus, yeah, you even do this programming first, yeah, basic programming, and then data structure, and then you learn DAA. Yeah. Actually, it should be DAA first, yeah. Yeah, but anyway, this is our syllabus. What can we do, yeah? Okay. So the improvement is like this. Oh, selection sort is so what to say is so slow, yeah. You need to find first the largest one and then exchange with the which one now, yeah. I mean that the eye, yeah, to get this is ascending like this, yeah. And and despite worst case, of course, the comparison is big O and square, yeah. So therefore, the idea if you can use any data structure that to do both A and B in log, big O log and time. Yeah. This big O log and time. So very nice then, yeah. Big O log and time. And then we can be very good, yeah. Balancing the work, achieving a better trade-off, and the total running time become big O and log n. And this is the idea. This is the idea. The idea. Okay, and then we have so-called heap. Yeah. Then because we talk about sorting, then become heap sort. So before we talk this, you can what is heap? Yeah? Just what is heap? Yeah. Of course, heap in computer science, yeah, not just heap or what, yeah. Because if you talk about heap, and this like this definition of heap, a disorderly collection of objects placed haphazardly on top of each other. Within a heap of cardboard boxes, large amount of or number of both objects or loose substance in a heap. Yeah, this heap, yeah, but of course we also want to see heap in computer science. Yeah, what is heap? So it is in computer science, a heap is specialist tree-based data structure. So it is data structure and it's tree-based and it is special. Yeah. It is essentially an almost complete tree, an almost complete tree that satisfies the heap property. You will have that heap property. In a max heap, for any given node C, if P is a parent node of C, then the value of P is greater than or equal to the key of C. We like it, yeah. Okay, I'll put it this. Within 100, yeah. So all of the children of 100 will be less than him. So 19 less than 100, yeah. 36 also this. And likewise, the children of 19 should be less than him or her. Yeah? 17 less than 19, 33 less than 19, and so on. Yeah. So only this. Only this. Right? You can check this. Yeah? So easy to understand this. Yeah. Binary heap data structure, you have A. It's kind of array. Kind of array. But no, this is binary heap data structure. Yeah, array. Yeah. It's array for binary heap data structure. Can be viewed as nearly complete binary tree. So just like this, yeah. All levels, all levels, except the lowest one are completely filled. Divide this, yeah. This is can be unfilled because this is filled, but this is unfilled. The key in root is greater or equal than. So if I have, for instance, 30, yeah, so it should be less. For instance, this is 15. Let's say this is 7. But and then if I have also 7, also okay because it's greater or equal than all its children. Yeah, this then this is become let's say 2. So the key in root it mean let's say the root is this 30, yeah 30. So be greater or equal than all its children, and the left and the right subtrees are again binary heaps. So it means okay 30 is correct. That is larger than all of the children, and then so on. 15 because it's the only one. I mean leaf, yeah, of course. Can it be compared? This the let's see the leaf. So it is empty. Of course, 15 is okay. Yeah? Okay, so this is the rule, yeah. So root is greater or equal than all its children, and the left and right is like recursive. Yeah? Again, binary heap. So you have two attributes, yeah. Length A, which is array, yeah. And then heap size A. Okay. Okay. Parent, this is index, yeah. Index. This is index. This is the element. So 16 is the element. And parent I, and then return. This is it's floor function, yeah. Return I over 2. Left return to I. And this, yeah. Yeah. I divide by 2. This, yeah, to I. This is to I times I. This is to I plus 1. Right? So parent, if I say parent, I mean the argument I, yeah, and then return I over 2. Left I return to I. Right I return to I plus 1. Then heap property, remember this is array, yeah, array index parent I larger than or equal to AI. And then if you have index, yeah, this, so this tree can be represented by this array like this. So you put from the beginning root, yeah, 16, yeah, and then 15, yeah, and then 10. It means layer by layer, yeah. The first layer is gray, second layer that is aqua or green. Okay, aqua. Okay, well, let's say this green, and then yellow, and then blue. Yeah. So 16, the traversing this, yeah, and then 15, and then 10, yeah, and then 8, then 7, 9, 3, yeah, and then okay, layer again 2, 4, 1, yeah. And the level you can see this, yeah, level 3, then level 2, and level 1. Remember uh, how to say, the leaves, yeah, the leaf in here, so it's from 0, then 1, then 2, then 3, yeah, for the level. Okay. You see, because there is a different color here to distinguish between that layer, yeah? Layer or level. This is 0 here, yeah, and so on, yeah. Okay. And you can check the property, yeah. Reparent I larger than or equal to AI. Question AI, this A5, yeah, this 7, yeah. Then parent I, parent I mean A2, yeah. A2, of course, 15 is larger than 7, and so on. Okay. Notice the implicit three links. Children of node I are to I and to I plus 1. You can see this. To I plus 1. Can be seen here, the index. Okay. Because I, for instance, 1, yeah. So it's to I plus 1, 3. Right? So parent I, then that children, if not I, then yeah, just one big, yeah. Not I, 16, yeah. 16 this is the root. I is 1. I is 1 is. Then of course the left one to I mean 15. Correct, yeah, to I this the index is 2 times 1. Yeah. Then to I plus 1. 2 times 1 plus 1, 3. That index. Okay. I and 2 I plus 1. Why is this useful? In a binary representation, a multiplication or division by 2 is left, right, shift. Correct, right? So this, yeah, this 4, right? But if it is this is 2, yeah. It is for division, right? For divide by 2, yeah. And likewise, if it is, sorry, this, yeah. See the bit, yeah, this is 8, right? 4 times 2 equal to 8, right? So it's very easy. You only go left, it means you have multiplication, yeah, go left. Then if you go right, it is division. So very easy. Yeah, in the sense of computing, wow, it is very, very useful, right? Because it is, I mean, anyway, computer is binary representation, yeah. Even though then, of course, you can develop. Yeah? So it's very useful property, yeah, by shift left or right, and then you will get multiplication and division. Adding 1 can be done by adding the lowest bit, because if it is 9, yeah, become 1, 0, 0, then just put 1, become 9. So easy, right? I is indexed into the array A. Binary trees rooted at left I and right I are heaps. Yeah, I mean, when the children of the particular root or particular tree which heap, yeah, it's also become heap, and so on. Yeah. My word. So I confirm that with in case my wife just text me. Dan tomorrow. So, okay, finish, yeah. Okay. So again, yeah, binary tree rooted at left I and right A, right EI are heap, yeah, of course, yeah, because children should be, if it is root, so everything to the left, everything to the right also heaps, yeah. Otherwise, it's not hold, yeah, this is the root. So this also heap, yeah, and also heap this. But AI might be smaller than its children, thus violating the heap property. So if it is, it means what? Okay, with this, yeah, yeah. For instance, if it is, if it is big one, yeah, because remember this is a big one, yeah, 16, 15. This case, for instance, 16, and then here not 15. Let's say this is, let's say 100, guys. So if the left is 100, it means smaller, yeah. Sorry. This is the case of if it is like this. I think this is a bit confusing. Yeah. Mm-hmm. Yeah. So like this. For instance, yeah, 16 and 15. But you can imagine if it is not 16 actually. This is, let's say this is 13. Yeah, it is not correct, right? Because root should be larger or equal to the children, yeah. But 13 is smaller than 15. It is not 16. In this case, let's say this is 13. So it is violating the condition. Right? So that's the case. So I mean, root should be larger than or equal to, yeah, children. Because this. Okay. So might be smaller, yeah, than its children, thus violating the heap property. And we have method so-called happy phi. Happy. Yang penting happy. The most important is happy, yeah. This is I think this very like even the music is also like this, yeah. Okay, the good. This. Okay, yeah. So happy five makes this array a heap once more. So because it is violating, yeah, I mean not correct anymore. It is wrong. It's not correct anymore. But you have happy five method makes a heap once more by moving AI, the one that's smaller, yeah. AI down the heap until the heap property is satisfied again. So don't worry, it's kind of readjusting. You can restructure or readjust like this. Okay. P5 n is total number of elements. This P5 AI array and then that index I. Left and right subtree of I are heap. Yeah, okay. Make sure it is. Then make subtree rooted at I a heap. Okay, left I, right I. Okay, correct, yeah. So L to I and then right to I plus 1. If L less than or equal to N and A index L larger than AI, then largest to L. L to largest. Else I. So which one? So if L less than or equal to N, then L to the largest, because we need to how to say, we need to make sure, yeah, that it is correct order. Right? And AL larger than AI. So okay, L become how to say that L, yeah, is L for that left and right. Remember L become the largest one now. Else that I then. If R less than or equal to N and AR larger than A largest, then R become the largest. From that is right. Then if largest not equal to I, exchange, because can be 7, yeah, and then 7. We don't need to exchange, right? But it is 7, yeah, and then because remember, yeah, once again, this 16 and 15, and actually this is um, 13, yeah, should be larger, yeah. Then need to follow. Then this is uh, 9. Yeah? Then need to exchange, right? Need to exchange this. Then become 9 and then 7, yeah, like this. Okay. Then exchange this, yeah, A index I with A index largest. Then once again, P5 with that largest, no. It's divide and conquer. I already taught you. So we just need, how to say, advancing the move by changing the parameter, like recursive. Example like that, yeah. So remember this 2 or whatever, this is the index, yeah. So I have 16, 4, 10, and so on. Yeah. And then you can check if the root, yeah, mean 2, yeah, this is index 2, yeah, this A2. It means the element 4. Why it is? We start by this because there is 14 here, and this is not correct, right? Because 4 is less than 14. Remember the parent, this the relation of this. Yeah, that this number, yeah, it is less than. 14. Right? Also, actually also less than 7. But because he said the largest, yeah, say largest. See the largest one. Yeah. This largest. So in a particular route, we will see the children. Which one is the largest one? Of course, 14, yeah. I mean index 4, right? Index 4. Okay. Then we need to exchange array index 2 with index 4. Yeah. I mean 4 exchange with 14. Okay. So exchange, yeah. So cannot correct 14 here. Then 4 in here. It is correct, right? That 14 now is larger than or equal to 4 and 7. It's correct, yeah. It's correct. Okay. And then recursively, this why we only need to modify the argument of parameter. Then we call P5 A4. It was P5 A, I mean array, index 2, no 4. Because we have to make sure, yeah, that this 4 also okay. I mean the element of this is index of 4, but this element of 4, yeah, should be larger than or equal to 2 and 8. Yeah. It is correct or wrong? And it is wrong, yeah. Because 8, yeah, 8 is larger than 4. So it is wrong. Right? It is wrong in here. Index 9, right? Okay, then exchange with 8, yeah. Because if in this case for 14, actually 4 and 7 is less than 14, but we need the largest one. If only one, well, actually the same, yeah. 2 also, a minute, yeah, yeah. So we need to see which one is, because it is only 8. For instance, if it is, in this case, yeah, in this case, of course, 4 and 7, 7 and 14 is larger than 4 in this case. And then see the largest one, get 14. But in this case, the second one here, the case, 8 larger than 4, but 2 no. So we don't care about 2 here. In this case, in number 1, called P5 A2, we need to find the largest one. But it's only one. So that's why 8, I mean index 9, yeah, need to be proceed. That's why we exchange A4 with A9. Yeah. Okay, then become 8-4. Yeah, this. And then recursively call P5 A9 because it is already in the leaf. Yeah, when this is the last one. I mean, of course, no children, so we are done. Okay, so easy after this example, right, guys? You know, talk about running time. The running time of AP5 on a subtree of size n, yeah, rooted at node I. So this is the root in node I. So this is a lot, yeah. Size n is so determining the relationship between elements. It is big data 1, I mean constant. Plus the time to run AP5 on a subtree rooted at one of the children of I, where 2n over 3 is the worst case, like this, yeah. The n less than or equal to t 2n over 3 plus that one. So Tn big O log n. It doesn't matter actually, as long as it is not only one. We'll talk later about this. Yeah? The partition. So it gives you worst case big O log n. Now alternatively, running time on a node of height h, big O h. Yeah. So if you have this, yeah, and then and so on, yeah. So this is the height. Yeah, of course, can be also calculated by big O h, yeah, the height of that tree. How to build a heap? So convert an array A index 1 until n, where n equal to length A, into a heap. Notice that the elements in the subarray A, n over 2 plus 1, and so on until n, are the one element heaps to begin with. Yeah? Begin with. Yeah. Because subarray n plus 2 plus 1, yeah, and n is one element have to begin with. Yeah, of course, yeah, you can check this in one particular. Let's say this divide by 2 like this, yeah. So this is 2i, yeah, this is 2i plus 1. Okay, so in here, yeah, this, yeah, when element have to begin with, yeah. So this is how to build the pseudocode with heap array A for I until this n over 2 down to 1. 2p5 AI. Just check the example, yeah. So I have A for 1, 3, 2, and so on, yeah, here. Yeah. And how to build the heap, yeah, just check this, 4. Yeah, yeah, 1, 3, yeah. And then 2, 16, 9, 10 is 14, x 7 is, okay. Then how to do? Because it is from array to 3, yeah. And how to make show this. Then check on screen. Okay, 4 is larger than equal to 1 and 3. Oh, correct. Yeah. 1 is larger than 2. Actually not correct, yeah. But here, because we will check until the like the it should be like the deepest one first, yeah. Actually here, yeah. So I know is from here, yeah, because it's the I would say like from the beginning, from the very beginning is the last one, yeah, the last one, yeah, the last one of that that three. Yeah. Check was 16 and 7. Okay, yeah, correct, yeah. 16 is larger than 7. Okay. So I is at index 5, yeah. Okay, and then move now here, yeah. So it is correct for this index 4 then, yeah. 2 is larger than equal to 8, larger than equal to 14. It is not correct, right? It's not correct. Okay, so you have to exchange just like what we did before, yeah. So this 2 and 14, we will exchange the largest one. Yeah? So okay, 14 are here. Correct, yeah. No, correct. This is correct. This is correct. Correct. This is also correct. And then we will check another one. Like next. Okay. 3 should be larger than or equal to 9 and 10. Which one the largest one? Of course 10, yeah. So we need to exchange this 10, yeah. Okay, then become 10 and 3. Okay. Okay. And then it is correct, yeah. And then no 4. Of course it's not correct, yeah, because in this case, actually go back again, yeah, go back again. Before this, actually go this, yeah. We'll find actually this because actually from after you say this is 14 is okay, yeah, 16 is okay, and then okay, the 10 is okay, yeah, and then it's kind of tag, yeah, here. This index 2 is not okay because 1 is less than 14 and also less than 16. It should be larger than or equal. And as usual, you need to find the largest one. It means 16, right? By our previous algorithm. Then, okay, exchange 16. Likewise, actually, you also need to change with 1. Yeah? But 1, if it is 1 here, yeah, then 7 in here. So you also need to exchange with 7. You got this then. 7, 1, and then 18, 16. Okay, after that, it's kind of a stack, yeah. So this is the root now. Okay, which one is the largest? Of course, 16. Mean to exchange the 4 with 16. And then, okay, correct this. Now, everything is correct in order, yeah? Okay. Okay, now the analysis. Correctness, yeah. Inductions on I. All trees rooted at M larger than I are heaps. Induction on I. Check this, yeah. Induction on I, anything you can check. And it's correct, right? Always larger than, yeah. Larger than. All trees rooted at M. Then check 14 this, yeah. So yeah, all trees then larger than I are heaps. All trees, it means if we, for instance, check 14, yeah. So this is 3, yeah, it is correct heaps. This is also heap. Then likewise this, if it is, I focus on 8. It is, yeah, the 3 of 2, the 3 of 4 also heaps. So induction on I, all trees rooted at M, any particular M, where M is larger than I are heaps. Correct, right? Okay. So if it is, for instance, in index 4, yeah. So anything rooted at index 8 or 9 also keeps. Is correct. For instance, rooted at okay, I see, for instance, 16, yeah. And then the index, no, it is I is 1, it is I is 2, yeah. So if rooted at M larger than I, so it means no I is 1, yeah. So here equal to half, from sigma I from 1 until infinite, I times x power I. So you have equal to x over 1 minus x square, yeah, over 2. And then sigma I equal to 1 until infinite I over 2 power I. Then half over a quarter, of course 2. Therefore, positive time is big O. It's comparable with that size. Okay. 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 Now you have analysis of positive A, you know. Positive is big O n. And then for I and don't know cost n times exchange of a constant big O1. This is also shifting, yeah, n minus 1 and then n. Okay, big O1 also constant. NP5, for instance, 1 log n. So the total running time of heap sort is big O n log n plus heap A time, which is big O n. Yeah. This is big O n. Okay, then we want to see how to do, yeah. If short, it's easy, yeah. Just take one by one, yeah. So okay, I exchange, actually not exchange, what is it? So 16, yeah. And then you put in that exchange with this, yeah. The last one is 1, yeah. Exchange this. Then you put this 16 here, yeah. Right. And then when you actually you mark this, okay. And then again, yeah, 14. The last, the root, yeah, 14. You will exchange with the next one. The smallest one. Okay. Then P5, and then actually 1 become here. Yeah, P5, and so on. Okay, not 10. Then need to put that the least one, yeah, these two. Yeah. actually need to book this this exchange exchange A1 with AI, this A1 with AI, because AI now from this from uh, the last one I, and then of course last one, and then now become 14, I mean the index is then 2, and so on 10, so A1 exchange with the AI that index I, okay, and so on, okay, 10 put it here, then 9 put in here, 7 8 8 put it in here, then 7 put it in here, and 4 here, and 3 in here, and then 2 here, 2 in here, yeah, 2 in here. Then last one, 1 again. You can cut it. So then we read traverse from root, 1, then 2, 3, label lah 4, 7, 8, 9, 10, 14, 6. So it is sorted. So that's the way for heap sort. Heap sort. It's sorted already. Sorted. Okay. Great. This was like, we know that this is very, very, how to say, this was like heap sort, like what to do. Very, very powerful. Okay. Okay, summary. Heap sort uses a heap data structure to improve selection sort. Remember selection sort that so slow, because you need to, when you are playing card, you need to again rearrange this, put in here, and make the running time asymptotically optimal. Running time now is big O and log n, like merge sort, merge sort. But unlike selection, insertion, or bubble sort, remember what's that? Big O and square, When for worst case, selection, insertion, or bubble sort. And then now sort in place, like insertion, selection, or bubble sort, but unlike merge sort. Remember, if merge sort, it is okay, powerful, but you need temporary or additional storage. No, here we don't have. You sort right away in there. You don't need any additional storage. You sort in there, in place. You don't need any additional one. Okay. The second part is priority queues. Priority queue, PQ. PQ. A priority queue is an ADT, again, abstract data type, core of data structure, core of data structure. For maintaining a set S of elements, each with an associated value called key. Special one. Set, remember set S of element, which each with associated value called key. Priority queue support the following operation: insert and then S, that kind of set S, with act with some element, particular element. Insert S with any element, any particular element. It means insert element X, insert S, and then it means S union with X, become this. I mean, you are add up something. And then you have another function. It is insert, with 2 arguments. Then you have maximum S returns the element of S with the largest key. I mean, the largest number. This returns the element, but without removing. To know which one is the largest key or largest value in your set. If you want to know and also remove, I mean extract max, returns and removes the element of S with the largest key. Extract max. What is the application? What is job scheduling? Job scheduling, share computing resources unique. Of course, which one is more important? Like how to say, the waiting time is so long, okay, just give you more priority, because otherwise when you finish. Even simulation, for instance, which one is the let's say the VVIP, for instance, VVIP first, VVIP, yeah. So it means to be served first, and then maybe VIP, and then maybe class, or to say business class, and then class stadium. As a building block for other algorithm, it can be used for any algorithm, other algorithm. And because we already learned about heap, so heap can be used to implement that priority queue. Okay, removal of max, yeah, takes constant time on top of EP5. Removing of mm, mhm. Yeah. Removal of max takes constant time on top of EP5. Only remove, yeah, and anyway, it is on the top, of course, constant, yeah. For instance, back again, yeah, in EP5, because anyway, EP5, I mean, this EP5, I have to say. This heap, yeah, the heap can be used, yeah, to implement a PQ. So just check again. So this, yeah, if you take this, yeah, the large one, easy, yeah. It is constant time. This, yeah. Rainfall of mark takes constant time on top of EP5, yeah. Big data log n. Yeah, because, okay, remove and return largest element of A. Yeah, this is the explanation or description of this function, yeah. What to do? A index 1, of course, become max, yeah. Okay. And then what to do? Yeah, and then okay, A1, yeah, I mean the first one, just like what we, okay, I will make it two, yeah, this, where is that thing? Yeah, yeah, yeah. This, okay. Easy, yeah. So A1, A1, yeah. A1 become X, yes, and then AN become A1. AN become A1. It means max this, yeah, 16 of course, yeah. And then AN it means what? This AN, this, yeah. And with this one become A1. So one become this, yeah. So one, I put it in here. Yeah. And then N minus one become N. I mean, this is like for the indexing, yeah, advancing the index. And then heapify A1. You make sure that the heap consistent to be heap. I mean, to make a correct, on the one remix heap, yeah, return max. Mm-hmm. Yeah, this become n log and become big data log n. Yeah. It's not that difficult because we already know what to do. Yeah, this, yeah, remove and put it this and then happify. Yeah, and like propagate until the root. Okay. Insertion of a new element. If we want to insert the new element for our priority queue, so we mean enlarge the priority queue and propagate, yeah, the new element from the last place up the PQ. From the last place up to the PQ. 3 of height log n, running time big data log n. So this is for heap extract mag. Yeah, because remember you have extract mag and then insert. Yeah, so with all this, okay. Maximum of course is the fastest one. Yeah, the fastest one maximum is fastest one. because this is the top, yeah. So mean A1, yeah, A1. This is A1, but also happy 5, yeah. This is happy 5, and then happy 5. After that A1, yeah, this A happy 5. Then because A1 no become the last one, yeah. And this. So no insert is the one that we discussed. This, yeah. If insert and E and the one to insert is this key. The key. So need to adapt one additional storage to insert. Okay. Then if size A, it become the I. It's the last one, yeah, I mean the last position. While I larger than I, while I larger than 1, yeah, any parent I less than key to AI, then A parent I become AI, then parent I become I. Then after this all, then you can cut key from AI. Check this all. Okay, this is heap, yeah, 16 and blah, 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 so on. Root always larger or equal to the children. Want to insert, yeah. With insert, it mean which one the last one? Because the index, the last one is here. Yeah. It means you plus 1, it can become here then. Yeah. This the last index, yeah. Then I not become here. That's why here, right? Okay. Then if you put here, yeah, that actually, which one? Actually, it is 15. Yeah. Actually, 15. This new one is 15. 15. Of course, happy 5, yeah. 7 is less than 15. Need to kick this, yeah. Need to kick this 7, yeah. Then you exchange 15 here, yeah. Then 15, let's say 15 here, yeah. 15 here, right? Then become 7 in here, right? Then 14 and 15 also wrong. Then to exchange this one, no. This yeah become it is propagate here, yeah. So here in here. And then it's correct, not 15 actually. 15. Okay. Okay, and then we learn about quick shot. After heap shot, then priority queue. I mean, priority queue actually implemented by heap shot. Heap, yeah. Non quick shot. What is the quick shot? Very nice, yeah. Quick shot. It's very vast. This. Yeah. Wait, there is any? Okay, maybe this. Yeah, quick shot. Animated visualization. Just divide and conquer. Yeah. Yeah, very efficient, but still, with worst case, big O and square. Once again, yeah, quick shot. Okay, random. Go. Like this. And then, okay, ice. Yeah. So what kind of, like kind of, what is that kind of a three shot, yeah. Then you work on this three shot, like kind of locally, yeah. And this, yeah, maksudnya this, yeah, like kind of time window, yeah, time window, or say like, uh, yeah, like a window, like a window. Okay, back to here, yeah. Characteristic sort in place. It does not require an additional array like merge sort. It's the best, the same like heap sort. Yeah, no need any additional array. Yeah. Call it sort in place. Like insertion sort, unlike merge sort. Yeah, insert sort also in place. Sort you have, yeah, remember you have to put an additional array. Very practical. Average sort performance, big O and log n. But worst case is usually big O and log n. But there is case big O n square. To understand quick sort, let's look at high level description of the algorithm. Divide and conquer algorithm. means like binary search or merge sort, a partition array into two sub-arrays. Similar, at least two, yeah. Sub-arrays such that element in the lower part less than or equal to element in the higher part. So like L less than equal to higher part. It's just like any binary search or merge search, merge search. Then conquer, recursively sort the two sub-arrays. Combine, trivial since sorting is done in place. Yeah, because it is in place, it means you don't need to do anything. It's already sorted in this particular sub-solution. Okay, partitioning linear time, partitioning procedure. This linear time. Partition APR. As usual, we divide by this P, this is R. So AR, I mean, you divide it by this. Yeah. The first one, you just comparing the last one with the first one. Yeah. Last one with the, so this AR to X. Then P minus 1 to I. J R plus 1. R plus 1. So it means J, yeah. J should be going here, yeah. J here. I going here, yeah. I to the right, J to the left, yeah. Right, R plus 1 J. While true, repeat J minus 1 to J. Okay, J go to the left until AJ less than or equal to X. Mean X larger than or equal to AJ. Repeat I plus 1 until X, this, yeah, X less than or equal to AI. If I less than J, then exchange AI exchange with AJ, mean the index and return J. See this, yeah? So I have 17 blah, blah, until 10. So just check this 17 with 10. So it means X, yeah, equal to this, yeah, because you need this is let's say this ascending from smallest into the largest. Easy, right? Which one is the smaller one or the least one? Of course 10, yeah, easy. Okay, then exchange. Okay, and now after you proceed, because it's in place, so it means next one this 5 and mean 12, yeah, and 5. Which one smaller? Of course 5, yeah. Okay, and then next one this 6 and 8. Which one? It is already correct, yeah, no need to do anything. Okay, next, yeah, this 6, yeah, 6. And then 19 and 8. Which one smaller? Of course 8, yeah. And then this. So see, in this particular window, yeah, this, okay, let's see like this. So all of the blue color always less than that orange color, over the brown color, yeah, brown color. 10, 5, 6, 8 always less than 23, 19, 12, or 17. Yeah, always. So you can make sense that, okay, this divide and conquer. Okay. Initial call. So this is the first one is linear partitioning procedure, partitioning. I mean, into two, yeah. So left less than right. Initial call quick sort A, sorry, and then from 1 until length A. APR, yeah, okay, you already know this, but I kind of merge sort, yeah. Q, and then R. And then you have Q here, yeah, so Q in here. I mean P in Q, yeah. And the other one, Q plus 1, yeah. Q plus 1 with R, yeah. Okay, like that, yeah. If P less than R, then Q, partition APR, quick sort PQ, then Q plus 1 R. So this is this is this. Analysis of quick sort, assume that all input elements are distinct. I mean, there's nothing the same. Yeah, I mean, 2, for instance, and then 3, and then 2 again cannot. Yeah, this is distinct. I mean, the assumption. The running time depends on the distribution of splits. Because if it is this and it is this, of course, different. This and it is, for instance, this, different. Best case, yeah, if we are lucky, partition split the array evenly. Yeah. So 2t n over 2 and okay, this is big data n. Divide like this evenly. This evenly. Yeah. Okay, this all n. So I mean on n, and then for the for every layer is log n. Yeah. So I mean totally big data is n time log n. Yeah. N time log n. Worst case. What is the worst case? One set of the partition has only some element, only one, this. And then the other one, the n minus 1, yeah, and then okay, big data n for this, this and this. Okay. So the n minus 1 plus this. Sigma k from 1 to n, big data k, sigma theta, big data, sigma k minus 1, k from 1 until n from k. It means if it is k, yeah, in a particular place, it means n square then, yeah, big data n square. So like this, yeah, skew. So 1 and the rest. 1 and the rest. 1 and the rest, and so on. It means what? It means we become very stupid, and because this become n, yeah, and here also n, right? This is also n, right? This. So n times n, yeah, n squared, then, yeah. Okay. When does the worst case appear? Input is sorted. So if you are sort something or is sorted, it is worst case. Or input is reverse sorted, but in the reverse order. Then same recurrence for the worst case of insertion, the same like remember insertion sort the same, yeah. I think Pak Budi already told it in my class. Of course, I told this insertion sort is very stupid if you have already sorted in the in the reverse order, but then ascending. Then actually you have this 4, 3, this 3, for instance 2, 1. If you wanna make it ascending, yeah, then reverse order you can very stupid because it means n time n, yeah, n time n square equal n square. Yeah. However, sorted input yield the best case for insertion sort. Yeah. If it is really already sorted like this, and you once again sorted, this only sorted is only one. Yeah? But if it is a quick sort, it becomes stupid because even though it's sorted, it doesn't know. Then once again, it will do, and then become equal n square. Right? Remember, comparing this, yeah, with 1 with 4, and then 2 with 3. Okay, n square, yeah. Insertion sort, no. Right away, you got, yeah, already sorted. Okay, analysis of quick sort again. Suppose the split is 110 and 910. 110 and 910, guys. 10% and 90%. Yeah, just n over 10 and T9 n over 10 plus that. Okay, big data and that we call it combined cost or match cost. Yeah? And see, even though it is a bit skewing, yeah, this 10 over 9 base log n. So it is like 10 base log n like this. Yeah, of course, this is all n. Yeah, this is alpha. Still, we consider is n log n. So this is log n. Actually, not pure log n. Actually, 10 over 9 base log n. But this consider log n. So still, this n, yeah, in n log n. Okay. So what does this mean? This is really cute, yeah. Okay, again, yeah. Okay, so suppose we alternately lucky and unlucky cases to get an affiliate behavior. This is lucky, yeah. You are divided by 2 partition. To you n over 2 and okay, this big data. And unlucky like this, yeah, L minus 1, and then we consequently get 2 power ln over 2 minus 1 big theta n over 2 plus big theta n to ln over 2 minus 1 and still n log n. The diagram like this. Okay, this is unlucky as we done only 1 and then the rest. But in this rest, and then you got, let's say, equal. So in general, we will call it log n. The total and log n. So that's what this is this, yeah. So all this, the height is log n. The layer, I mean, so to say the distribution of layers the log n. And then of course this n. So what does it mean? So it means as long as it is not 1 all the time, yeah, 1 and the rest, or the rest and 1. As long as it is not all the time, you will get big theta or pico log n. It is because average, yeah. I mean, okay, big theta and log n. Always. Because I don't believe, and I think it is already been proven in statistics, yeah, that it is impossible to have only 1 and the rest, or the rest and the 1 all the time. Okay, maybe only 1 and then, okay, this is kind of maybe 10%, 90%, maybe, okay, let's say 70%, 30%, and so on. So in average, like, yeah, this was like big data in average, big data and log. Yeah, that's the good of quick shot. Of course, the worst is big O for n square, yeah, n times n is the worst. I mean, only 1, yeah, and then the rest, or the rest and 1. So this average case scenario. How can we make sure that we are usually lucky? Partition around the middle and of a second element, or partition around a random element works well in practice. So usually this random element, yeah, work well in practice, yes. Like this, guys, yeah. If you decide by this, of course, it is most likely this will be okay, lucky. Or random, maybe here, maybe here, or maybe here, whatever, yeah. Random is okay. Okay. Of course, like half like this will become, we think that's okay, but even random is okay. Okay. But as we the worst is only 1 and the rest, yeah, or the rest and 1. Okay, randomized algorithm running time is independent of the input ordering. Yeah, it is randomized. No specific input triggers worst case behavior. It's good also. Yeah. No specific input triggers worst case behavior. So very how to say, like very rare. Yeah. Those case is only determined by the output of the random number generator. The output of the random number generator. Yeah, so for randomized quick shot, the thing of how to say, the partition point, yeah. Okay, assume all elements are distinct. Then partition run a random element. Yeah, random, yeah, that's why this partition run a random element. Consequently, all split 1, like 1 and then the rest, yeah. 1 and minus 1, 2 and minus 2, and minus 1, 1 equally likely with probability 1 over n, of course. Transformation is general tool to improve algorithm with bad worst case, but good average case complexity. Actually, many cases like this, yeah. When I taught in the special topic, yeah, many we use randomization because really, there's thanks God, yeah, that our could not give us. We thought this randomization, guys. Oh, our life is so difficult. Yeah? Everything certain and make some algorithm become very bad. Yeah, that's why if algorithm have worst case, yeah, with bad worst case, so algorithm have bad worst case, yeah, but have a good average case complexity. So just use uh, randomization, yeah, and will improve your algorithm, yeah, result. Okay, this the pseudocode, yeah, partition APR. I think we don't need to just randomize the I mean, which one I want to cut where, here or there. and then exchange AR with AI with AR. Then return partition. Remember the partition already we discussed the partition. And this is randomized partition to which one you want to cut. Yeah? And then randomized quick sort this P less than R. Then okay, you put this randomized partition first. This APR randomized partition, and then randomized quick sort. Okay. So only this different. This is the same. APQ A Q plus 1 R. Okay, this thing, yeah. So that's why very interesting, yeah. I mean that DAA guys, yeah. That I wish that you have how to say can also apply yeah, in our real life, yeah. That maybe the idea, of course, it's not necessary all the thing, but the idea really is for me is amazing that this thing can be keep us many how to say insight, yeah. Okay, that's it, yeah. That's our lecture today, yeah. That which we will also need, yeah, this for the next lecture. Need to I think okay for the FEL3, yeah, 14, yeah. But if cannot, then use the 17, yeah. I will let you know, yeah, about our WhatsApp group. Okay, because yeah, as said, I think in the beginning of fasting, people of Indonesia is so weak that they cannot stand, so they need off day. Yeah. While we are in abroad, even I remember fasting, we still go see so many beautiful girls or handsome boys, so many delicious food, abundant everywhere. Yeah. Even I remember the time when we are celebrating Idul Fitri or Lebaran, even we need to go to campus, when some of us need to take exam, need to because it is exam, so you have to morning you go for sholat Id, yeah, for Jamaah Id, and then you are right away in hurry go back to campus and take your exam. Yeah, I don't know, I forgot it is midterm or quiz or final exam or whatever. Yeah, this yeah, and then we feel okay. Yeah, Inshallah, I think we never cancel. We never cancel our puasa fasting. It's okay. But anyway, it is a policy that we need to follow. So if 12 until 16 April we cannot go for our lecture, and unfortunately in 14, yeah. So I just move in 17, yeah, in Saturday, yeah. And because it is okay for you, yeah, you can choose class C or class D or class E or E or IUP, whatever. Yeah, just don't forget to tick your attendance list. So it's okay. Only me, of course, it's quite hard for me from 7 until 6. Yeah, it means how many? This is 11, roughly 10 or maybe 11 hours. Yeah, because I need to take rest in 12 until 1. Yeah, usually like that. So around 10 hours consecutively. But anyway, that's the life, guys. Yeah, sometimes we cannot avoid. Yeah, just face the problem, solve the problem, and then continue our life. Yeah, for me, like this, I don't like to run away from the problem. Of course, sometimes we also want to run away. Who doesn't want? Yeah, sometimes we just want to run away. Yeah, but anyway, like or dislike, we need to solve the problem. Yeah. Okay, so okay, that's all, guys. Yeah, so I will see you, inshallah. Yeah, we'll see. Then maybe 17. Yeah, if, next week cannot. Yeah. Okay, stay healthy, guys. Make a prayer, make a dua that Allah, our good Lord, may our good Lord lift up this pandemic as soon as possible. And also, I ask you to pray. May the vaccination, yeah, smoothly going through, and then we can back to our normal life, yeah. Because I also very miss the normal life, yeah. That's all, guys. Okay, have a nice time. See you, guys. Thank you. Assalamualaikum and good afternoon, guys. See you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, sir.
Thank you. See you. See you, guys. See you.
Thank you.
Okay, thank you so much, sir.